V naught R is equal to I naught R, V naught C is equal to I naught into chi C, and V naught L is equal to I naught into chi L. They will both be traveling in the same direction, in phase with each other. This is current, this will be voltage. Impedance just means it is the net effective opposition that is offered in a series LCR circuit. So that is known as impedance. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about alternating current and what happens when alternating current is passed through a resistor, inductor and a capacitor. Now what will happen if I pass an electric current where all of these components are arranged together in a series fashion? So let's get right into it. So what exactly is a series LCR circuit? A series LCR circuit just means that an inductor, a capacitor and a resistance is connected in series where AC power source is supplying the current to that particular circuit. So this is known as a series LCR circuit. We saw what happens to the voltage and current when it was kept separately. Now all of them are put together. Now we are checking what is the difference. Is there any difference? Is the resistance being offered? Is the resistance a combination of all these, or is there any difference in that particular connection? So again, there is our AC power source which supplies a voltage of V, which has a peak value of V naught, is now surging through this particular circuit where current I is passing through with a peak value of I naught. And we have an inductor L, a capacitor C, and finally a resistor which has a value of R. So first things first, we'll write down what we know, that is the current can be represented as I is equal to I naught sine omega t plus phi. Again, this plus phi just indicates that current is either leading or lagging behind this particular voltage. That is, voltage is indicated as V is equal to V naught sine omega t. So that plus phi is just the phase difference between current and voltage. So if there is no phase difference, we can say that phi is equal to 0. If there is a phase difference, just like in the inductor or the capacitor circuit, we can say current is leading behind pi by 2 or current is lagging behind pi by 2. Like that we can say. So just as a precaution, we are keeping this phi there. For now, we don't know that if current is leading or lagging behind this particular voltage in this circuit. So as a precaution, I'm saying that, okay, I know V is equal to V naught sine omega t is the voltage in this particular circuit, which means that the general equation for current that is passing through this particular circuit is given by I is equal to I naught sine omega t plus phi. So that plus phi can be 0, can be pi by 2, can be minus pi by 2. I don't know, but I'm going to find out with the help of phasor diagrams and a few equations. So I do know one thing, the first equation that comes to my mind when there is voltage and current present, that is Ohm's law. So I do know that the peak value, that is peak value of so we can actually say that this is an inductor of value L, this is a capacitor of value C, and that is a resistor of value R. Now I'm going to check what is the relation between voltage and current that is passing through each of these separately. So I can say that V naught will be the peak voltage. So when that peak voltage is passing through this particular resistor, I can say that V naught is passing through resistor R, which means I can apply Ohm's law, V is equal to IR, and simply say that the peak value of V naught or voltage that is passing through the resistor R is equal to, this R is just there to indicate that this is the voltage that is passing through R. You can call it as V R naught or V naught R, anyways you like. So it is equal to, what is the equation? IR. So we can write I naught into R, which means here the peak voltage that is passing through the resistor R is given by V naught is equal to I naught into R. That is the first equation. And now We'll also see what is the peak values of voltages that is passing through the capacitor and inductor. So again, we can say that the peak value, again, peak value of V0, let's say the capacitor V0C or CO is equal to I0 into, is it C? No, it is the resistance or opposition offered by that particular capacitor. So what is the opposition offered in a capacitor? We found out in the last class, that is chi C. So we can see that it will be equal to chi C. So I0 into chi C. Now again, the same for an inductor. The peak value is V0 into L, which is equal to I0 into chi L. So this will be the equations relating the voltage and current in these particular circuit. So if I consider them separately, each of these will be having voltages passing through them. Don't forget about the previous chapters that where we studied connections in series and parallel, which means now they are connected in series. So I can write this particular equation like this and let this relation be here. It is just Ohm's law applied to each of these individually. Now what we are going to do is that whatever we have learned in this particular chapter, that is phasor diagram, is going to be applied here. So how do we apply phasor diagram? So first let's draw a phasor diagram. So initially I'm going to consider the phasor diagram of a purely resistive circuit where current and voltage are in phase with each other, which means they will both be traveling in the same direction, in phase with each other. This is current, this will be voltage, and the phase angle between them, or the phase angle that makes with this particular axis, is nothing but omega t. The phase angle difference between these two is 0 because they are in phase with each other. So this is for a purely resistive circuit, right? Now it is not just purely resistive circuit that is here. It is a capacitor and an inductor that is slammed together in series, which means I am going to draw the phasor diagrams of the capacitor and the inductor onto this very same diagram, and we'll make some modifications so that we'll get a new phasor diagram. So what is the speciality about the phasor diagram of inductor and capacitor? In one, current is lagging behind 90 degrees, and in the other one, current is leading by 90 degrees. So I can say that in one, current is actually lagging behind 90 degrees, and in the other one, current is leading by 90 degrees with respect to voltage. Let's say this is voltage. If this is voltage, then we can say that this will be the combined effect of. So if you look at the previous classes, you know that this is a combination of all the three graphs which we have drawn. That is, this is combination of all the three separate phasor diagrams all put together in one. So we'll get an image like this one. So the angle between this one and this one is nothing but 90 degrees, which means current is leading by 90 degrees. Here, current is lagging by 90 degrees. So there is a capacitor and there is an inductive circuit here, and there is purely resistive. So all together it is slammed here. So this will be VL, this will be VR, and this will be VC. So these were the different circuits. Let's say there is a difference of phi. Okay, the phase angle difference, let it be indicated by phi. General way of writing it is no problem, because here the phase angle difference between voltage and current is simply 0 because they are in phase with each other. But generally we can write omega t plus phi. There is no problem in that. So yeah, now these two are at an angle of 90 degrees. These two are at an angle of 90 degrees. And remember what a phasor diagram is. A phasor diagram is nothing but a rotating vector diagram, which means it is a vector quantity. We can apply all those laws of vector addition in this particular diagram. Or simply I can say that since the line or the length indicates magnitude and these two are vectors lying in opposite direction, I can use vector addition, which means two vectors acting like this will have a resultant. Since this vector is slightly small and this vector is slightly larger, the net effect of this particular vector will be in this particular direction. right? That is, vector VL and vector VC together will only act, the resultant of these two vectors will only be in this particular direction, right? If you remember vector addition, it will be easier. So I'm just applying vector addition here. That is because I want to create a relation between all these three quantities. When they are lying like this, I cannot create a relation between them. So what I'm doing is that I'm applying vector dynamics, vector formulas here, where these two vectors will yield a resultant vector. Since these two are lying in opposite direction, the one which is having more magnitude, it will be going in that particular direction, because the pull is in one direction and the other direction. Whichever person is pulling more harder, the motion will be, or the resultant will be in that particular direction. Since this length is more, or the voltage that is applied along the capacitor will be more, because capacitor stores some charge, right? So this will be the resultant direction, not this long but slightly. So this will be the resultant direction. I'll show you. So generally I can say this will be 90 degrees, this will be 90 degrees, that is all known. So what I'm going to do is that first I am solving modulus of, so it is VC minus VL, which means I'll have a resultant in this particular direction. That is the first thing we are going to do. So in doing that, I will get a new phasor diagram, that is. So again, if I take the resultant of these two vectors, that is solving these two vectors, I will get the output as this particular value, or simply the phasor diagram will change to this particular form, where this will be VR and the net effect resultant will be acting along this particular direction. Or simply we can, so again we can just simply say that this particular diagram, that is the phasor diagram, is now the resultant of these two added together, or the resultant of these two vectors. Again we know one more thing, that is the length of each of these vectors will give you the magnitude value, that is the peak value of those vectors. For example, here if I take VR, the length of VR is equal to V naught R, which means it is the magnitude value or the peak value. Here again, if I take this peak values, then I can say that VC is actually equal to V naught C and VL is actually equal to V naught L, which means this quantity, that is VC minus VL, is actually equal to V naught C minus V naught L. That is the net peak value, or the difference can be indicated like this also. Now again, all this is true. Now what do we do? Now the thing is that since these two are again two vectors acting at two particular angles, or these are two slanting vectors with respect to this particular axis, we can say that if one force is exerted in this particular direction and one force is exerted in this particular direction, we know that the resultant will be somewhere in between these two vectors. Or simply saying, if two vectors are acting at a particular angle, then the resultant vector will be in between those two vectors. In this particular case, I'm assuming that, okay, somewhere along this line is the resultant vector. So I'm calling it as resultant vector V, and simply I'm saying that the magnitude of this particular resultant vector, let it be V naught. Let it be V naught. So this will be the resultant. Now what I'm doing is that I have three vectors here, right? Now I'm going to apply the triangular law of vector addition. If two vectors can be represented as the two sides of a triangle, then this third side will give you the resultant. So in order to find out the resultant here, that is V naught, I'm going to make this particular thing into a triangle. So for that, the easiest thing I can do is that take this particular vector and move it here so that it makes a triangle. So I'm going to take this and move it here so that it makes a triangle. So I can apply triangular law of vector addition. So this is V naught, the entire length or the peak value. Again, I'm going to take this and move it here so that this makes an entire triangle. So this will be, this side will be VC naught minus VLO or VL naught. So we have a triangle here. So we have this particular triangle right now, which means I can find the resultant value of that particular V naught. So that is what I'm going to find out. So again, this particular triangle, if I take it, let's say I'll draw this here so that you can clearly see that. So this particular triangle now is like a right angle triangle where this distance is nothing but V naught. That is, this is nothing but the altitude and this is nothing but the base. So I can simply say that this will be equal to V naught C minus V naught L, and this will be nothing but VR naught. This will be nothing but VR naught. Now it's very simple. We apply Pythagorean theorem to this particular triangle. So we know that we want to find V naught. We know what is the altitude and we know what is the base. So again, we apply Pythagorean theorem, which states that hypotenuse square is equal to B square plus altitude square. V square plus altitude square. And we know that the hypotenuse is nothing but V naught. So V naught square is equal to B square, which is VR naught square plus V naught C minus V naught L whole square. So this will give you the resultant. Now from this point onwards, everything is just mathematics. The pure aspect of physics actually stop here when we solve the vectors from this. Now it's just applying triangular law and just doing some math. So how do we solve this? It's very simple again. We just have to substitute the values to all of these. So we do know that V naught R is equal to I naught R, V naught C is equal to I naught into chi C, and V naught L is equal to I naught into chi L. So we are going to substitute these values to this particular equation and we'll get the answer right out. So again, while substituting, we'll get this particular result, that is V naught is equal to I naught R whole square plus I naught chi C minus I naught chi L whole square. So again, if you look closely, you have an I naught common here. So we'll take that I naught square outside of the root. So I can write it as V naught is equal to I naught into root of R square plus R square plus chi C minus chi L whole square, and this I naught I can take it to the left hand side, so it will be V naught by I naught. So we know that V by I is equal to R according to Ohm's law, or the ratio of voltage to current is nothing but resistance. So generally what we are trying to do is that we are trying to calculate what is the resistance offered in an LCR circuit. Since if that is not clear for anyone, I'm just putting it out there. So this will be equal to root of R square plus chi C minus chi L whole square. This particular quantity is now known as impedance, that is indicated by the capital letter Z or Z. So this Z is known as impedance. Impedance just means it is the net effective opposition that is offered in a series LCR circuit. So that is known as impedance, and this will be equal to root of R square plus chi C minus chi L whole square. That is These three quantities, that is resistor, capacitor and inductor, when they are connected in series, their effective net resistance offered in that circuit is known as impedance, and impedance is found using this particular relation. Impedance is denoted by capital letter Z, and this is the formula for impedance. There is one more trick or one more way which you can actually find impedance, and that is using the impedance triangle. So this particular triangle, I'm going to redraw it here. Okay, I'm going to draw it very clearly here. So let's say this is our triangle. This triangle is also known as impedance triangle because it is a relation between VR and the rest of the components that is being used, that is the resistance, capacitance and inductor. All three are within this particular triangle, which means the effective resistance will be given by this particular hypotenuse. So that is why it is known as an impedance triangle. Let's say the angle here is phi, and we know that we are going to find out this particular hypotenuse, that is impedance, and this particular length is nothing but V0, V0 R, and this is nothing but chi C minus chi L. So again, here it is this particular voltage and here it is the difference of this particular quantities. So I have just written down in terms of resistance. You can also use R also, it is completely fine, no problem. So from this triangle we can actually say that tan phi is equal to opposite side, which is chi C minus chi L divided by V0 R. V0 R, or just simply V0, is equal to tan phi, or simply phi is equal to tan inverse chi C minus chi L divided by V0. So this is the particular way you can find the impedance and the angle for this particular impedance triangle if the question is asked like that. But mostly we can say that the only thing you actually require is this particular equation where resistance, inductor resistance, capacitor resistance and normal resistance are actually given together. So you can take this particular relation and get the net output, that is the net impedance of a particular LCR circuit. So again, to quickly sum up, the only thing we do is that consider the LCR circuit in series pass a voltage, that is alternating voltage, through that particular circuit, and we know that we can express using Ohm's law the peak voltages as such, and from that we go to the phasor diagrams of all these different quantities, that is inductor, capacitor and resistor, and we know that they have a phase angle difference in between them, so we draw them together and then we solve those vectors and then we rearrange them and get an impedance triangle, or simply we can say that we get a triangle with two sides being vectors, which means we can actually apply triangular law of vector addition, and finally we can find what is the resultant of that particular triangle, or we can just simply say that what is the net resistance or net opposition offered by this particular LCR in the circuit. So then we will find that that is equal to root of R square plus XC minus XL whole square, which is actually equal to the net resistance or simply impedance in this particular case. And we can also find that using the impedance triangle from the relation phi is equal to tan inverse chi C minus chi L divided by V0. So that is also one way of finding it, but this is the most simplest way. I hope you have understood everything about this. I'll meet you all in the next class with one other topic. So I'll see you all in the next class with some power equations and working principles of certain other quantities. Until then, thank you.